Astrophysical Jets, what are they?
Perfect. Okay.
With us since about 1979, when one such stroke in the sky was observed at visible light, which nobody understood. Thin, long thread in the sky, which was soon followed by further discoveries. In the meantime, we know hundreds of such thin threads. They were called jets because they look a bit like the jets coming out of airplanes, subsonic, supersonic ones. They're pushing jets which drive the airplane. Until today, there is no uniform understanding of how they function, but certainly they look similar to what we see, particularly in the evening in the sky when airplanes are crossing. And there's no uniform understanding how nature blows them in the sky, in contradiction to the jets from airplanes, which our engineers have constructed and which function and perform as wanted and drive the airplanes from side A to side B. In the sky, apparently, they come mainly from stars, young stars, sometimes white dwarfs, neutron stars, and even in much stronger, much larger form, from the centers of certain galaxies, called active galaxies, active galactic nuclei, where it's not clear to my colleagues how these engines function. They speak of supermassive black holes, and I think they should speak of central burning disks which act very similarly to rotating stars, namely magnetized objects rotating around their spin axis and thereby changing their magnetic fields, shearing the field, leading to reconnections, which make relativistic electron-positron plasma, which is necessary to blow the jet. This plasma will be lifted, will be accelerated by buoyancy from the center of a heavy body to its outskirts. It will then be post-accelerated by the low-frequency magnetic waves emitted by the rotating magnet again. And then all that's required is a de Laval nozzle, first just suggested by Blanford and Rees back in the 70s, last century, so that they go from chaotic, subrelativistic to supersonic, ordered, and then propagating loss-free through enormous distances in the universe, the longest of them being several million light years long and almost moving at the speed of light, which I think the driving particles are electrons and positrons, transrelativistic speeds, relativistic electrons and positrons, in total neutral and in total free of current and magnetic field, only with local co-moving electric and magnetic fields, which allow a loss-free transport through large cosmic distances.
Okay.
They are found throughout the sky at daytime and at nighttime. They are seen at radio waves particularly, sometimes also at optical or even at X-rays. There are hundreds of them in the sky when we look closely. They have various lengths from solar system size to huge galaxy cluster size megaparsecs. You should take a look at a few of the examples which I will show you. They look different one by one. Some look simply straight line, others look U-shaped or S-shaped, some look distorted, and often they end in huge bubbles called lobes. In all cases they're elongated, sometimes quite thin, in other cases quite bulky. The closest jets we see are in nearby star-forming regions of our Milky Way galaxy. So they come from young stars like our Sun, and we think that our Sun, when it was young, also acted as a star-forming center. So it's the young stars rotate faster than older stars. As they rotate faster, their magnetic fields are stronger. They make more pair plasma, push it harder, and so they make jets on the scale of young solar systems, where we occasionally see dozens of such jets in one picture.
Quickly about the history of jets, just so people know, what is your experience working with jets? So when did you start looking at jets, and why are your opinions and your thoughts on jets relevant to other people? What is your experience in the field?
In 1979, when jets were first mentioned in astrophysics, I was just a young member of our Bonn Institute for Astrophysics of the university, and our neighboring Max Planck Institute with its Effelsberg telescope brought the first maps, radio maps of jets seen in the sky. People were surprised, they didn't understand what was going on, so I was immediately challenged to think, have my thoughts about how to form them. In those days, in collaboration with a British team, Stephen Hawking, Roger Penrose, Dennis Sciama, were also young astrophysicists who noticed these new discoveries. So for us it was a lively time to find out how nature can produce such creatures, such features in the universe. Creature is of course the wrong word, because I don't think they are alive, but they look various like creatures. So it was misexpression, but still.
So you mentioned quickly that they were found through, they were taken, the photographs were made with a radio telescope. Can you talk a little bit more about how we see jets and how we create the images that we are showing today?
Yeah, now we come to the details of their structure. Usually the brightest feature in the sky is not the jet itself, but only its origin. The central place where it is made, that is the strongest radiator. So we see bright spots in the sky, which when we look more closely are elongated, with one end being bright and then a jet getting fainter as it moves away from its central source. At large distances, these jets usually get distorted, they get wiggly, curved, and often merge into large radiating lobes, where apparently the matter that has blown the jet is arrested and reorganized in terms of gyrations inside of large basins or lobes.
So you talked about how the jets bend near the end. Do they make sharp turns, or is it more of a general? So because it seems at the beginning they're very straight usually. What is it that changes and bends?
Very good question. They often look as though they had very sharp bends, but that may be an error of projection. We don't see this three-dimensional jet, we see it projected to the plane of the sky. And in this projection, comparatively mild bend can look very sharp. So the pictures show sharp bends and mild bends, but the propagation usually is almost at the speed of light of the matter that blows it. So for this matter it would be very difficult to make sharp turns. If we think in 3 dimensions, they are almost straight line.
When it comes to these jets, I think you already said this, but how fast in general are they traveling? How quickly do they elongate?
This is a question that has not yet been unanimously answered in all cases, but we express the speed in terms of the Lorentz factor, the relativistic Lorentz factor, little gamma, which is unity for subrelativistic motion, and which can become arbitrarily large for supersonic relativistic motion. This Lorentz factor usually is found to be between 100 and 10 to the 4, which means that the individual particles are 100 or even 10 to the 4 times more energetic than their rest energy. It's electrons and positrons moving at 100 to 10,000 times their rest energy. According to Einstein, energy equals mass times velocity squared of light squared.
Okay.
Concerning particular sources, we have not yet had conversations directly related to the pictures which we will show later. So in those cases we have to distinguish between stellar jets and galactic jets, galactic scales, which come from the centers,
Okay.
which are larger and the surroundings. So that will be the main distinction between, we could say, small jets and large jets, but the larger ones are farther away, and so they look similar to this, even though they are much farther and then much longer, and also different in their shapes.
Okay. Then we should talk about that quickly. Just, are there different types of jets, and if so, what is the difference? So what are the names? And what's the main difference in the?
Right, I should have said this before. We have 4 different classes of jets with, as far as I know, and as far as everybody knows, jets from young stars, from white dwarfs, from neutron stars, and from the center of active galaxies. The first 3 of them look in a way similar, because they're always driven by an object of stellar mass, whereas the last mentioned ones, they are sometimes 1,000,000 times more energetic and much longer, last much longer, coming from the centers of galaxies, where they are continually fed by the inspiring matter in the disk of that galaxy. So when we in the sky we see them projected and of similar lengths, but of course the jets on galactic scales are much more energetic, much longer lived, and have slightly different shapes and different interactions with their surroundings. When they encounter heavy matter, they are bent, they are turned, whereas if they come from nearby stars, they go more or less into clear space around surrounding young stars. In both cases, I think they are produced by rotating magnets, but most of my colleagues in the case of the centers of galaxies would talk of supermassive black holes, which I think have no way of doing it, because black holes swallow, they don't spit. So I think these jets coming from the centers of galaxies are created in a quite similar way by the magnetic fields which rotate in the galactic plane and are enhanced towards their centers, where they create the necessary pair plasma that blows the jet afterwards. So even though the sources are different, the jets which they create then often look similar. But you should look again at the cases which we've seen right now on screen, or which we will still show you.
Okay, but you said there were 4 different types of jets?
Right.
What are the 4 different names? So are there 4 names for each type of jet, or is it just...
No, there are not different names. Often it is not really clear from the beginning. We only see a jet and have not identified the source that blows it, because the jet is seen at radio frequencies, and whilst the source may have been seen by X-rays or in the optical, or maybe also as a radio point source. These jets are visible when they interact with ambient matter, when they collide with the surroundings, and so that in regions of clear sky, the jets are not very bright, they're not very conspicuous. Usually what is brightest is the central engine, the source from which they come, a bright spot in the sky, which often has very little structure, just bright spot. But then occasionally jets encounter obstacles further out from the central source, and we speak of knots in the jets, where they are bent, and finally at the very end, where they again hit into some obstacle, we speak of the heads of the jets, the place up to which they have forced their channels, and there again we get a lot of radiation because the ambient matter is heated, is forced to radiate, and we see also a lot of radiation in different frequency bands. So not always do we see a jet similarly from its source through its channel up to its final ending place, the head. Often it looks different at the source and at the termination point, the head. And a lot of work has gone into trying to map. In a few cases we have succeeded in mapping the jets on many scales with different enlargements, but that always was a lot of work of the observers who had to enhance the faint radiation sufficiently to make clear pictures.
Okay, so you talked about, do you need the paper in your hand? Or can you just, yeah, because it looks better when it's just on the side.
To hold on to.
you talked about you've talked about different parts of a jet. So you've talked about the origin and the head. Can you just very generally sort of define the different pieces of a jet? So when you look at a jet, what are the pieces that you can distinguish?
Okay, maybe you compare a jet to a lawn sprinkler. In the case of a lawn sprinkler, we have a three-legged object in the garden from its with a hole at the top, from which you get a sparkling water beam. In the case of the jet, it's not water, but probably relativistic pair plasma. But otherwise, the two are quite similar. The matter that is forced out from the valve of the lawn sprinkler then moves in the gravitational field of the Earth and makes a more or less long beam of water, which eventually terminates when it runs into obstacles like trees or bushes or simply the outsides of your garden if you have forced it too strongly. So jets can be compared to water beams, except that water is then has a much higher mass density. Water is 1,000 times heavier than air, and air is again heavier than relativistic pair plasma. So it's a factor of 10,000 or 100,000 times in mass density. Jet is a very light medium, and as a jet is very light, it reacts also more sensitively to mild perturbations from the environments, from the surroundings. But otherwise, just compare relativistic jets in the sky with non-relativistic water beams in the garden.
Good. That's a really cool comparison, I think. But what can you just quickly say, because then we could show a picture and this could be really cool. You could say, when you look at a jet in the sky, when you look at a picture or radio, the radio photos of a jet, what do you see? So you see that there's an origin, and then you just see that there's the jet itself, and then is a head. Is that all that there is?
Almost. In reality, you see usually a few knots in between, which you left out in your question. So we have the origin, the core of the jet, which is always visible if we see the jet at all, and the central part of the jet, usually much brighter than the more distant parts. And in the end, as you said, the termination. But in between, on long jets, there are occasionally a number of knots where the jet had temporarily more resistance with the surroundings than otherwise. So core, knots in between, several of them, and finally termination, and possibly a whole big lobe in which all the jet material is then assembled and gets to rest.
Cool. And then also, when looking at jets and some of the pictures that we've seen of jets, it seems like there is just a jet on one side of the origin. Are jets always on both sides from the origin, or is there only sometimes
Good
one?
question. I didn't mention it before. Each engine produces one upside and one jet going upside. Oh, jet. Very good question. Usually, an engine that drives a jet produces two jets, one, say, towards above and one towards below the accretion disk for the central rotating magnet. So we have a central rotating magnet defining a plane, and there are two jets, one above, one below. So we speak of twin jets. However, when both jets are moving almost relativistically, we often only see one jet and not the other side. So in most of the mapped jet sources, we only see one-sided jet, but we have clear indications that the opposite, the receding jet, likewise exists, but is not seen. So the mapping shows one, even though there are always two opposite jets leaving the central engine.
And why do we not see the other side?
Relativistic beaming, it's a problem of Einstein's already special theory of relativity. Objects that move almost as fast as light radiate mainly in their forward direction, hardly in their backward direction. So we only see the approaching jet, not the receding jet, by relativistic beaming.
Yes. I'm trying to think of if there's anything else that we wanted to talk about.
I get the impression you mentioned everything, but let me check. I left the black holes as much aside as possible because I don't want to be polemic here. It wouldn't help. And a vacuum producer of pair plasma, or it's not important for those who don't know it, and the insiders know it anyway. So I think the way how strong is our understanding, and some don't understand it all, and others make it very. I don't think that helps for this first. If you cut what we've done, I think that's almost now half an hour and not 10 minutes already. So
no, we can.
A few things were. What I said first, I think, was almost the best in the sense of language. Later I was already getting a bit tired, but shorter questions which were easier to answer. Some of them I think I answered satisfactorily, others not so much. But the first session was already something like 3 or 4 minutes, and all the others added. You easily fill 20 minutes with what we've done.
Mm-hmm.
But if we take pictures on top of that, it's 25 minutes. So it gets a long movie.
Yeah, well, I mean, I would cut it down to probably 10 minutes. Pretty easily,
Then
I think.
we should have enough material
Yeah.
for 10 minutes. Because
10 minutes? Yeah, so with this you could make 30, 40 minutes. That's how much we filmed. But if you want to keep just what's very interesting and what's very well said, then we cut it down to 10 or so minutes.
I think it would, in the sense of how people would enjoy it, you optimize by having it not too long.
Yes.
You're quite right. My aspect of a scientific aspect, which should not be the leading one, even then I would say you touched upon a number of important. Yeah, you touched the thing that it's twin jet, which I forgot completely in the first session, and you touched the beamed radiation, that quite often we see something, some of the heads we don't see because they're probably also beamed and not in our direction. So others they look different, different heads look different. I think simply because we see them from different directions. They're not isotropic, which is rare in astrophysics. Usually when it's a star, it shines isotropically. So these jets are different from other astronomical objects in quite often radiating anisotropically, so that only certain observers see them and others don't. From the same type of head, we can get very hard radiation or no hard radiation at all, depending on the orientation of us with respect to the jet. So jets are not as easily mapped as, say, stars, which are mainly hot glowing spheres. Here we have one-dimensional, essentially one-dimensional objects preferentially radiating into forward directions, which can look quite different from different directions.
I do have one more thing.
The first public conference was in 1979, organized by Jim Gunn, United States, who had seen this one-sided jet of the galaxy 3C273. So jets came rather suddenly when radio telescopes were more careful in sampling the sky. So the physicists became suddenly aware that the sky does not only contain stars and galaxies and groups of galaxies and that's it, but that there are very different looking sources radiating not necessarily in the visible domain of the spectrum, but rather in the radio domain or also X-ray domain. So the general awareness of jet sources in the sky, I think, can be dated in the late 70s and culminated perhaps only 10-15 years later, when astronomers had many more telescopes, many higher resolutions, higher sensitivities, so that they could map the different shapes, different colors, different hardnesses of the radiation which they emit, which can go from the radio all the way into the hard gamma ray regime, which I didn't mention much before, but which happens when the jet runs into an obstacle, terminating obstacle near its head, and then radiates even hard gamma rays, like cosmic waves. Was this a full answer? You said...
Yes, just the history.
The history, yeah. So, yeah, since then there is a flow of information, news sources every year, but headlines are getting rarer now. People repeat, and theory is behind in this case. I think there are certain groups which try to understand these phenomena, try to mimic them in computers, but I think they may well be on the wrong track. Jet sources cannot easily be simulated with computers unless one has a simple set of describing equations, quantitative descriptions of their motions, and for this fundamental questions must be answered first, like what are the media, what are their energy spectra, how does nature make them. Only then may we come to the conclusion. We can describe them very, very simple equations, not statistically, stochastically, but rather by clear analytic equations describing their motions under simplifying assumptions on their surroundings, on the interactions with the surroundings. Details also about their channel walls, which can emit spectral lines like in SS433. But now we come into details which are rare and special sources which are better understood and which I think go very nicely with all the other understandings, but need time to become commonplace knowledge.
Good. Could you just one time say who you are, and so say your name, and then what sort of your education sort of and your experience in the field, just once very generally.
All right.